Good afternoon. Welcome to the second lecture of the Vehicle Aerodynamics section of the module. Before going into the module, I want to bring to your notice a couple of things. One is the Blackboard site. So when you go into the Blackboard site for the module, you have a learning materials section. In learning materials, you have aerodynamics, vehicle aerodynamics. And in that one, you have weekly lessons. In weekly lessons, you have weekly study plans. So from this week onwards, you will see that now if you go to week 1 of that plan, so you have curriculum resources. So in the curriculum resources, you see the lecture material, lecture presentation, pre-recording. So pre-recording is what I'm putting now, and the lecture recordings on the day as well. So in the lecture recordings, what we do during the lectorial, I record in parts. So none of these parts go beyond half an hour time anyway. Okay. And a new feature will also come into this. So that is a study plan for the week ahead. So what I'm going to do is I'm going to put study plans for each of these weeks. So you will see what is in there. So the study plan links to those study plan material for week 1, week 2, etc. that I have. And this today's lecture is comprised of 2 parts. Today's this week's session comprises of 2 parts. One is the lecture, so which I do in PowerPoint, and then there are some supplementary notes for you to understand. So we will go through the note in the classroom. You can have a look at it now after the lecture, but we will go these parameters are needed for you to do the tutorial questions. So tutorials are also linked into here. So when you go to curriculum resources, you will see that there will be a lecture, there will be lecture recordings, and then there will be a section for tutorials as well. So that section will be that section will contain tutorials and tutorial answers. So that's how this will be done in the coming weeks. So then we will go on to the main lecture itself. I guess you can see this. So in the in this lecture, what we are trying to do is what I'm teaching is fluid. I'll give you the fundamentals of aerodynamics. So that includes fluid mechanics. Fluid mechanics, in the sense it is part of applied mechanics. So in fluid mechanics, you will have fluid statics and fluid dynamics. So you have done these and some of these sections earlier. Fluid dynamics in year 1 perhaps, and then there is aerodynamics or fluid mechanics and aerodynamics. Aerodynamics is also a subset of fluid mechanics. And it's a branch of dynamics actually, branch of dynamics that deals with the motion of air and other gaseous fluids. So aerodynamics is always going to deal with gases and air. So it doesn't involve liquids, so it doesn't involve any liquids, only involves gases, and it always contains the word dynamics. That means there is always movement, so it's not static. So you don't say aerostatics, you just say aerodynamics. Yes. There is a field which is called aerostatics, but we are not learning that. We are learning aerodynamics. And this is necessary to understand the aerodynamic flow over a vehicle. So this is a car, say, for example, and it is moving in this is a car. It's moving in the forward direction, and there is a high pressure zone here, so that's the speed is low here, and then due to the shape of the car, the fluid accelerates over the body of the car. So in here you see some acceleration, and around in here you have the highest velocity. That means because of the Bernoulli's equation, or because how the Bernoulli's equation works, you have the highest velocity here, but the total energy has to be conserved. Therefore, your pressure here at the top lowers, it goes down. So you have the highest velocities over the roof, and you have the lowest pressure around there. Then in around here at the back window, near the back window, the flow decelerates. That means pressure increases again. Then here again you have a high pressure zone and a low speed high pressure zone. And here what you will find is actually a low pressure zone. And underneath the car, there always has a low pressure zone. That is because the flow is accelerating underneath the car. That means there's a high velocity here. That means low pressure. So this is the reason why you like the performance vehicles to have a very low ground clearance. Very low ground clearance means you will have very high speeds, air speeds underneath the body of the car. So when you have very low speeds underneath the body of the car, you will find that because of the high speeds, there is the pressure there goes down. That means you have negative lift force here, meaning the force exerted on the car is downwards. That means it will help the car to stick onto the road better. Okay? So in other words, it will increase the weight of the car in a sense, but that is good because when you have downforce like that, the stability of the car is better and the handling of the car will be better. Okay, then we will look at the aerodynamics or effect of aerodynamics. So I'm looking here at two bodies. One is a streamline body, the other one is a bluff body. So we talked about this in the last lecture also. So streamline bodies are characterized by attached flow. So the flow is attached to the body, and bluff bodies are basically detached. When in the sense the flow around the bluff body it detaches quickly. That means you will have a depleted pressure zone or a negative pressure zone here, larger one than a streamlined body. And when you have a body contour like that, and when air flows over a body, something forms over that which is called the boundary layer. So what this means is that the velocity over the just above the surface is 0, and around here so this line is normally drawn at 99% of the free stream velocity line is that. So that is called the boundary layer. So this notation is important for you to understand the boundary layer effect and the forces acting upon a car. Okay. So when you talk about external flow, the external flow is due to undisturbed air velocity is equal to the road speed of the car. Okay, and on car body, a boundary layer forms like earlier, as I said earlier. Now this is due to viscous effect. So it's a thin film adjacent to the wall. So when we draw this one, it's an exaggerated diagram. It's a thin film actually. The boundary layer normally is regarded as inviscid, and inside the boundary layer, the velocity reduces from h velocity. H velocity is the velocity at the at the edge of the boundary layer. Okay, not at the edge of the solid. It's at the edge of the boundary layer. So the edge velocity is normally taken as 99% of the free stream velocity. So the free stream velocity in a car, in a moving vehicle, is the speed of the car. Okay. So for example, if you have if a car is moving at 100 kilometers per hour, the boundary layer is where you have the air velocity 1 kilometer per hour. Did you get that? That means the car is moving and the air is stationary. So, but at the boundary layer, air is moving with the car at speeds of 100 kilometers per hour to 1 kilometer per hour in that range. So inside the boundary layer, velocity reduces from edge velocity to at the wall to 0. So the flow accelerates over the top due to compression, okay, and decelerates in the rear due to expansion. So as I said earlier, if you look at the car here, so flow accelerates here, flow decelerates here, and this is high pressure, accelerating, decelerating, high pressure again. It's low pressure here. So the flow separates at corners and at the back. Flow separation means there will be reverse flow. So if you have reverse flow, there is a wake downstream. Okay, that's a wake. Okay. Then we will look at internal flow. So internal flow is for a great example is the pipe flow. So it is wall bounded, okay? And external flows are not wall bounded. Internal flows are wall bounded, and the boundary layer grows along walls. So there's the boundary layer here. There's the boundary layer there, and through the internal boundary, the mass is conserved. So there is mass conservation. So center line velocity increases along the path when you have a boundary layer. So if you had an average velocity of 1 meter per second here, usually it goes to 2 meters per second in the center, and here it becomes 0. So often bulk velocity is defined, which is mean velocity at a cross section. So the bulk velocity is the velocity, the average velocity of the pipe flow. So the center line velocity is larger than the bulk velocity, and the velocity at the walls is basically 0. Then we define what you call the Reynolds number. So you must know for internal flows, Reynolds number would have been RE equals rho V d over mu, but for external flows it would be rho V infinity L over mu. So now in here L is the length scale. It's a length scale, and for internal flow it's the diameter of the pipe. If it is a pipe, analogous to a pipe, it's a diameter. Then we look at inviscid and incompressible flows. So hydraulic head is the total is defined using the Bernoulli's equation. Hydraulic head is what you write as H in the Bernoulli's equation. So it defines the hydraulic head, defines the local static and dynamic pressures. Okay. So assuming all streamlines apart from the free stream, total pressure PT will be constant. So with no loss, we can write PT as P infinity plus 0.5 times rho V squared. Okay, or PT is P infinity plus half rho V squared. So here V infinity is the free stream velocity. And this means that static pressure increases when velocity decreases. Now, when the velocity decreases, now PT total pressure is a constant. So therefore, when the velocity decreases, your static pressure increases. Okay, when the velocity decreases, static pressure increases. And if you at zero velocity, you have P infinity equals V total. So this pressure is called total pressure or static pressure. So at stagnation conditions, stagnation means there is no velocity, the fluid is not moving. At stagnation conditions, your static pressure is equal to total pressure. So this is an example of inviscid flow and inviscid and incompressible flow application. So this is what you call the Pitostatic tube. In here, you have the P infinity there. You have the P naught at the nose tab. So this gives you the difference between P naught and P infinity. So usually here, your V is equal to 2 times Pt minus P over rho, the square root of that. So we will look at the viscosity effect. So the figure gives a schematic view of the boundary layer along a thin flat plate. So this is dimension in y direction is much larger. Okay, so in this one, so it's enlarged. So what you have here is a wall, and that's the free stream. So this region is the laminar region. This is the transition region, and this is the turbulent region. So, so in the laminar region is steady. Fluid particle moves parallel to the wall. So here fluid particles move parallel to the wall. Boundary layer glows slowly, yeah, and thin. And then in the turbulent region, so unsteady random movement of fluid particles, and it's not parallel to the wall. Remember, this is parallel to the wall. This is not parallel to the wall. Boundary layer grows according to rapidly and thicker, right? So it grows rapidly and thicker. So this is much rapid. And the transition region is where the transition takes place. So it's a blend of laminar flow and turbulent flow. So it's always intermittent, and you can model this in CFD, or you can look at this. Well, it's difficult to see it actually with the naked eye, but you can visualize it using CFD software. So there are some important parameters like the free stream, constant pressure P infinity, and velocity V infinity. In the case of pressure gradient, region far from the boundary layer will remain as same as free stream layer. So boundary layer thickness given in by delta is, as I said, is the 90 is where the velocity is 99% of the free stream velocity. In some books it says 99.5, but we will stick to 99%. So this is a function of streamwise direction x. So free stream velocity and fluid velocity, and different formulae for lamina. So for example, delta is proportion times 0.5 for laminar flow, and delta times 0.8 for turbulent flow. Okay. And so even though a transition region is a region, so it's a region, it's not a point, but normally for calculation purposes we ignore the transition region, and you consider it to move from laminar region to turbulent region at some point. Okay, so we'll take it as a point even though it's a region. So a local Reynolds number, a critical Reynolds number is defined where that transition takes place. So REXTR means the Reynolds number at which transition takes place. Okay. So for smooth flat plate, for a smooth flat plate, Reynolds number is 5 times 10 to the power 5. So don't consider this with the Reynolds number of 4000 for pipe flow. Okay, so this is not the Reynolds number for free stream flow is that 5 times 10 to the 5. For pipe flow, it's 4000. Okay, so around that. Okay, so so forget this 4000 Reynolds number for the, aerodynamics. You need to stick to 5.10 to the 5 Reynolds number. And look at this one. Now here, what you see is what you call flow separation. So flow separation can take place both in laminar and turbulent regions. So what happens is now that's your boundary layer. Boundary layer grows and grows, and at some point so you have recirculating streamlines. That means the flow is separating from here. So there is flow separation here. So in here, so your pressure gradient is goes down, goes below 0. So at the separation point, mathematically du over dy is becomes 0. Okay. So at this point, shear stress is 0 beyond that point. So this is attached flow. This is the separation point, and this is the detached flow, or the separated flow. Then we define two important elements called one is the friction drag and the pressure drag. So consider, so this is a streamline. So that's a streamline. So that is the angle. Angle psi is the angle of that streamline to the normal. Okay. So if you consider a panel that has ds size, ds width, so the pressure force or the frictional force is actually tau w cos psi times ds. Okay, so cos psi times ds, cos of that would be your frictional force. And if you want to look at the pressure force, so that will be ds, the area, times sin psi, okay, sin psi times p. P is the pressure. So pressure times sin psi times ds would be your pressure drag. So you have calculated the shear drag and the pressure drag. Now these two account for the total drag. So total aerodynamic drag. Remember, this is total aerodynamic drag. It's not the total drag, total aerodynamic drag. Okay. So your total drag, total aerodynamic drag will be dF plus dP given by these equations. You need to remember that your dP is much smaller than dF. So what for a aerofoil case, your dF is much greater than dP. But for a bluff body, your dP is predominant. For a bluff body, dP is predominant, not dF. So when you do a vehicle aerodynamic study, your pressure drag is quite important. But for the total drag, if you want to calculate the total drag, you need to include the tire or road drag as well. So you need to include that to calculate the total drag. So now here, that's your friction drag, that's your pressure drag, and this is where you want to have the total aerodynamic drag. Yes. And drag coefficient for now this is the drag coefficient CD, and this is a Reynolds number RE. So these are for smooth aerofoils. So this is for a flat plate, entirely flat plate. So these values are flat plate turbulent, smooth flat plate turbulent. Now this is laminar. So these are some aerofoils, similar aerofoils that give you different values. And then I would like to mention some relationships that are important to you. So for a 2D aerofoil, length L and of length L and width B, your CD is the drag coefficient is defined as the aerodynamic drag divided by 0.5 rho v squared BL. Okay. So for a flat plate, CD is normally 2.656 over RE root when it is laminar. For transition and turbulent, this will be between here and here. Your CD would be 0.148 over RE to the square 0.2. So for an aerofoil, you can define an empirical formula by curve fitting. Okay. And these are some figures where you have CP values against different angles. And this for the flow over a 2D cylinder without and with separations. Now this is without separation. This is with separation. Now this is the CD versus RE diagram. So for a vertical flat plate, using as reference. So this is for the vertical flat plate. So this is for the this is for the cylinder. So that's for the cylinder. That's for the vertical flat plate. Then you can look at the forces and moments on a car. So that will be your pitching moment. So that will be your rolling moment. That will be your pitching moment. That will be your yaw moment. So that is your longitudinal flows. That is your lateral flows. That is your vertical flows. So this is rolling. This is pitching. This is yawing. Okay. So if you look at forces and moments, lift coefficient is divided by the lift force over rho over 2 v squared A. Drag force is defined by the CD, that is drag over rho over 2 v squared A. And the pitching moment is you divide the pitching moment by the by rho over 2 v squared A. And for the lateral force, the lateral force y, you divide that by the same amount. And for rolling moment and for the yaw moment, you do the same. And then lateral stability. So that angle that is created by the lateral force is so wind. The wind tends to rotate the vehicle in clockwise direction. Due to that, that's the angle is the wind direction basically. So any decrease of CN is acting anti-clockwise direction will turn the vehicle back. So you need to look at that. So this finishes the first part of the lecture, and then what we will be doing is we will look at basic properties and turbulent bound layer, etc. So these notes will be there for you to refer to, and we will use these notes for the tutorial questions. So thank you for listening to this lecture today, and we will get on doing work in the lectorial class on Monday. Thanks.